Swayam Prabha, free DTH channel for education.
Next topic in the differential equations, ordinary differential equations. So this is once again we are going to talk about a second order ordinary differential equation. So this is we have already seen the Legendre's equation. Now we are going to see the Bessel's equation. So for Bessel's equation, what we are going to see is that we are going to see the some of the applications first. Okay, then we'll go for that. So where it is used. So Bessel's equations are used. It is one of the important PDEs in applied mathematics. Okay, and you can see that applications like you can see that in electromagnetic waves, in cylindrical waveguides, okay, heat conduction problems, electronics and signal processing, where you will use this Bessel filter, or you can do that like Kaiser window is there where they do that signal processing, etc. Similarly, for FM synthesis also they use the Bessel equations. Apart from that, in sound mechanics like acoustics also, in acoustic problems also they used to sound engineers and other people. So they also use that acoustics problems and some of the problems which we use it for in sending the rockets, okay, where the acoustics will be playing a role. So there also we will use this Bessel's equation. And then for finding the Schrodinger equation solution also this Bessel equation for some particular cases. Apart from that, diffraction from clinical objects, for example, DNA. So these are also some applications of the Bessel equation. Or we can say Bessel's equations are used as a tool to solve some of the problems. So let's see what is the Bessel equation. So the Bessel equation is the second order ordinary differential equation of this kind. So x square y double dash plus xy dash plus x square minus mu square y. Okay, x square minus mu square y equal to 0. So this is the Bessel's equation where mu is non-negative real. Mu is non-negative real. So mu is greater than equal. Mu is non-negative real. So you can see this already we have seen the Frobenius method. So you can clearly say that x equal to 0 is not a ordinary point. It's a singular point, and you can verify that it is a regular singular point because b of x. This is my p of x is nothing but I can rewrite this as x square by x by x square. Okay, so that is going to be x, and q of x is 1 by x, and q of x is going to be x square minus u square by x square is going to come. So if I just multiply this by x into p of x and this by x square p of x, then we are going to get analysis is going to come. Therefore, you can use the Frobenius method. So the solution is going to be x power r into is going to come. But we can x equal to 0, but x equal to 0 is regular singular point. Okay, x equal to 0 is regular singular point. So you can just directly use that Frobenius method where you can use that y equal to x power r summation m equal to 0 to infinity am into x power m is going to be one of the solution. Okay, the second we are going to find. Okay, so we can apply the Frobenius series and then we can find the solution. That's what we are going to do. So let us find the solution of this. So y of x is x power r into am x power m, and y dash is going to be summation m equal to 0 to infinity m plus r into x power am into x power m plus r, and y double dash is going to be summation m equal to 0 to infinity m plus r into m plus r into m plus r minus 1 into am into x power m plus r minus 1. So y dash and y double dash. So we can substitute that. So that what I'm going to get, if I substitute over here, then I'm going to get x square into, so I can write this as x square y double dash. So that is going to be summation m equal to 0 to infinity m plus r into m plus r minus 1 into am into x power m plus r, because x square is there, r minus 2 is there, so those two will get cancelled. Okay, and then xy dash, so again plus summation m equal to 0 to infinity m plus r into am into x power m plus r, because x into y dash, here r minus 1 is there, that's what I is going to get cancelled. Plus here x square into am, so I'm going to get summation m equal to 0 to infinity m plus r into am into x power m plus r plus 2 is going to come, because x square is there, minus summation m equal to 0 to infinity m plus r m plus r, just a, okay, am into x power m plus r plus 2, okay, and here there is no m here, am into x power m plus r. Okay, so you can see that there are 3 terms with x power m plus r. Okay, there are 3 terms with x power m plus r. So 1, 2, 3. So these 3 are with x power m plus r term, whereas this term is with x power m plus r plus 2. Okay, so I'm going to replace this one as m plus r term. So that is what I will do is that I'll just shift these two 2 onwards. Okay, if I shift that to 2 onwards, for example, we concentrate only this one. Okay, we are going to rearrange this. How are you going to rearrange? Okay, so we are going to rearrange a little bit. We are going to start that from m equal to 2. Okay, we are going to start this from m equal to 2. Instead of m equal to 0, we are going to start this one as m equal to, from m equal to 2 and most. Okay, so everything is fine. So x square is there, xy dash is there, x square is there. So here, what term is there? Where is my minus? Yeah, minus is here. Okay, and here u square is there. U square is there. Okay, so equal to 0, equal to 0. Now I am going to make this little bit adjustment. Okay, m equal to 0, that I am going to make a little bit adjustment. Remaining things I can submit up. Okay, I'm going to keep only the this one as a separate. Remaining thing I'm going to set. So I can write summation m equal to 0 to infinity. Okay, so these 2 terms I'm going to work out. Sorry.
Sir, the v square nu squared term, how did it become x power m plus r? It should be only x power m, right?
Here x power r is there, right?
Oh.
Y equal to x power r is there, right? X
Yes,
power
sir.
r into m equal to 0 to infinity a into x power r. Therefore, x power m plus r. Okay. Okay. So I'm going to simplify this further. So I'm going to take only a x power m plus r term. So that is going to become like m plus r into m plus r minus 1 into, here once again m plus r is there, plus m plus r, and here minus mu square is there. Okay, I hope everything is fine. Yeah, into okay, this is fine, yeah, into am into x power m plus r. Okay, so only this term is remaining. Okay, only this term is remaining. So that I'm going to write it separately. Summation m equal to 0 to am into x power m plus r plus 2. Okay, equal to 0. So I'm going to adjust this one a little bit so that I get the everything as n plus r. Okay, so let us see what is the adjustment now. So if I simplify this further, okay, so I'm going to get this is going to become like, I get to simplify this. So m plus r, if I take it out, then I'm going to get it like, so if I take m plus r in both of these terms together, okay, so then this is going to become like m plus r. If I take it common, so m plus r minus 1 plus 1 is going to come. So 1 going to get cancelled. So this one I'm going to write the summation m equal to 0 to infinity m plus r whole square minus mu square, okay, into am into x power m plus r plus this term. Okay, this term I'm going to do a little adjustment. Okay, what I'm going to do is that m equal to 0 is there. So instead of that, if I start m equal to 2, okay, m equal to 2. I'm going to start from m equal to 2 to infinity. Okay. If I start m equal to 2 to infinity, then first term is actually a0 is going to come. But if I put m equal to 2, that means what I got to do is here I got to put m should be going to m minus 2. Wherever I have m, that should go to m minus 2. Then automatically, whenever I put m equal to 2, this will become like 0. This will become like corresponding term will come. Okay. So therefore, m equal to means wherever I have m, that you just push that to m minus 2. So this is going to become like a m minus 2, and this is going to become like x power n plus 1. Okay. So this is the term I am going to get. That means there is first term and second term will not be contributed from here, okay, because it is already starting from m plus r plus 2. So first term and second term is not going to be getting contributed from here. Okay. So I can write that as two things. Okay. So I can write this as erase the rest of the things. So I can write this as first two terms are having some not common here. So first two terms I'm going to write it separately. So in that case, m equal to 0 case, that is going to become like r square minus u square into a naught into x power r is going to come. Okay. Plus second term. So r plus 1 whole square. Okay. R plus 1 whole square. R plus 1 whole square minus u square into a1 into x power r plus 1. Okay. Plus remaining term, I can just sum it together. M equal to 2 to infinity m plus r whole square minus u square. Again, I can take the same thing here. So m minus 2, I can take it. Okay, into am here, into am plus am minus 2 into x power m plus r equal to 0. So now let us take this one, okay, x power r coefficient. So if I compare the x power r coefficients on the right hand side, then I have r square minus u square equal to 0 is going to come. Therefore, there are two possibilities: r equal to plus r minus u is going to come. Okay, there are two cases: r equal to plus r minus u is going to come. Now we have the second one. Okay, so this is for x power r coefficient. So if I compare the x power r coefficient, I am going to get this one. Okay, if I compare the x power r plus 1 coefficient. Okay, so I have x power r coefficient. If I compare, I have r equal to plus r minus u is going to come. Now if I compare x power r plus 1 coefficient, okay, x power r plus 1 coefficient, if I compare it, then I am going to get r plus 1 whole square minus u square extra is going to come. So that is going to become like if I put r equal to mu. Okay, so there are two cases. Suppose, so this is going to become like r square plus 1 plus 2r minus u. Okay, u square. Okay, is going to come. So if I substitute equal to 0. Okay, so if I substitute into a1 equal to 0. Okay, so here why I am choosing here r square minus u square equal to 0, because as per the Frobenius method we need to choose a naught not equal to 0. Okay, a naught not equal to 0 is required. Therefore, we are going to do that. Okay, so this is the case. Now here second one, r square plus 1 plus 2r minus u square. So let us consider one case. Let's consider r equal to mu case. Okay, if r equal to mu, then I am going to get this is going to become like u square plus 1 plus 2 nu minus u square into a1 equal to 0. So u square get cancelled. So I am going to get 2 nu plus 1 into a1 equal to 0. So if I put nu equal to, so there are two possibilities: either a1 equal to 0 or 2 nu plus 1 equal to 0. Okay. So if I put 2 nu 1 equal to 0, then I am going to get nu equal to minus 1 by 2. Okay. But if you remember on the first one, okay, in the first slide or second slide, we mentioned that nu is a non-negative real number. Okay, nu is a non-negative real number. Therefore, nu is greater than or equal to 0. We mentioned. Okay, but here nu is minus 1 by 2. So therefore, this is not going to be the case. So only possibility is that a1 equal to 0 is the case. Okay, so when r equal to nu, a1 is going to become like 0. Okay, second case. Okay, case number two. When r equal to minus nu. When r equal to minus nu, this is going to become like once again u square plus 1 minus 2 mu minus u square equal to into a1 is going to become 0. Okay, so in that case, u square cancels. So minus 2 nu plus 1 into a1 equal to 0. So in that case, what I'm going to get? I'm going to get either a1 equal to 0 or mu equal to 1 by q square. If I take a1 not equal to 0, then I can either a1 equal to 0 or mu equal to 1 by 2. So in both cases, I am not going to get any conviction. So I can choose mu equal to 1 by 2 and then I can proceed. That is also okay. So suppose a1 is not equal to, suppose I choose a1 not equal to 0, then I can just say that mu equal to 1 by 2 is one case, which is going to okay. Okay, so now let us discuss only this case first, okay, and then we'll go for the second case later. So due to this r equal to nu, we are going to get a Bessel function, which is of first kind. We are going to get it. So let us keep this case now. So let us see this one. Okay, so let us keep only this one. Okay, and remaining things will just okay. So remaining things like this there is. So we are going to deal with only r equal to nu case. So we have when r equal to, so after solving these two equations, we got r equal to nu. So r equal to nu, I got to use it over here. Okay, so I have another relation that. So now I got to compare the x power m plus r coefficient. So if I compare that, then what I am going to get m plus r whole square minus u square into am plus am minus 2 equal to 0 is going to come. Okay, so therefore what I am going to get, I am going to get am equal to minus am minus 2 divided by m plus r whole square minus nu square is going to come. So if I substitute m equal to nu here, what I am going to get, I am going to get m nu square will come. Okay, that is if I substitute nu here, this is going to become like m plus r whole square, m square plus 2m r. Okay, 2m r is nu, so 2m nu minus plus nu square is going to come. Nu square will get cancelled, so we are going to get minus am minus 2 divided by m plus m square plus 2m nu is going to come. Okay, so I can just simplify this further. I can take m out, so that is going to become like m into m plus 2 nu is going to come. Okay, so that is nothing but my am. So I found the recurrence relation. Recurrence relation is am is equal to am minus 2. So we already know that okay, r equal to nu means a1 equal to 0. That we already know. Okay, so therefore, if I find a3, what you can find? So let us case one is odd case. Case one is odd. Okay, so a1 is already 0. And if I calculate a3 is going to be a1 minus a1 divided by something is going to come. Okay, I don't care what is going to come. So a3 is going to be, of course, it should be not equal to 0. So yeah, 3 you are putting, so this is going to be not equal to 0. So not a problem. So a1 is already 0, therefore this is going to become 0. And if I put a5 is going to be minus a3 divided by something is going to come, but a3 is already 0, therefore this is going to become 0. Similarly, a7 in terms of is going to come, but a5 is so etc. If you take any a2k plus 1, okay, if you take any a2k plus 1, and k is a positive integer, then you can say that this is going to be 0. Okay, means all r terms are going to vanish. All r terms will vanish. Okay, so a2k plus 1 is going to become 0. Therefore, all r terms will not survive. They will just they are going to become 0. Okay. So now we got to deal the even case. So for even case, what we are going to get? Okay. So r terms are going to become 0. Now we are going to deal with even cases. So for even case, what we are going to get? Once again, a0 we don't know. A0 we assume that. So a0 we assume that not equal to a1 is not equal to 0. So a2 is going to become like a2 is going to be minus a0 divided by 2 into 2 plus 2 nu. Okay, so 2 plus 2 nu. So that I can write this minus a0 divided by 2 square. I'm just taking 2 out into 1 plus nu square. Now a4 is going to be minus a2 divided by 4 into 4 plus 2 nu. Okay, so this I can write as minus a2 divided by 4 into 4 is nothing but 2 square. I can write 2 square, and I'm going to take another 2 here, so that is going to become a 2 cube into into 2 plus nu. Okay, 2 plus nu is going to come. And A2 is already minus A0. Okay, so in A2 is already minus A0 by 2 square. So this is going to become like minus into minus plus is going to come. So A0 divided by 2 cube into 2 square into 2 plus nu into 1 plus nu. Okay. So that is going to come. So I'm just going to take 1 over here. Okay, I'm going to take A0. I'm going to write this is 2 power 4 into 2 plus nu into 1 plus nu. I'm going to write because I'm going to use it. Some factorial is going to come over here. That's the reason. Okay. So now similarly, if I take A6 is going to become like minus A4 divided by 6 into 6 plus 2 nu is going to come. Okay, so I can write this as again. I just use this term again. Okay, so that is going to become like minus A0 divided by 6. I can write as 2 into 3. Okay, so 2 into 3 into again I'm going to take 2 out here. So 2 is going to come out, and this is going to become like 3 plus nu. Okay, and this I can write as 2 power 4 into 2 plus nu into 1 plus nu. So this is going to become like minus A0 divided by, so 2 power 4, 2 power 5, 2 power 6 is going to come. Okay, so 2 power 4, 2 power 4, 2 power 6 is going to come into 3 into 2 into 3 plus nu, 2 plus nu, 1 plus nu is going to come. So in general, if you take A2, okay, if you take A2J, okay, if you take A2J, you can claim that, okay, if you take A2J, this is going to become like minus 1 power j into A0 divided by, so wherever 6 is there, I have j is there. Okay, j is there. Wherever I have 6, I have j is going to come. That is not that. J10 is okay. Not a problem. Okay. So if I take a power 2j, then in that case I have written 2k there. So if I take 2j here, what I'm going to get? Wherever I have j here, this is going to become like 2 power 6 is there, so 2 power 2j is going to come. Okay, or I have written 2k there. Okay, whatever it is, not a problem. So 2 power 2k is going to come. Then into, so you can claim that this, you can easily guess that this is going to become like, so 6 means 2j is going to come. So 6 means 6 by 2 is 3. So this is going to be 3 factorial. Therefore here you can expect that this is going to be j factorial. Okay. Similarly, it is starting from 3 plus nu. Therefore here you can expect j plus nu. Okay. Into j minus 1 plus nu, etc. is going to come into 2 plus nu into 1 plus nu is going to come. So you can observe the pattern how it is something. Okay, so that here I have written, instead of that I'm writing it as I'm just simplifying it. Okay, so you can this is going to come, so that's not going to come. I have given some more expansion over there, but this is going to come. Okay, so at the end this is going to come. So 2 power, so if I put instead of wherever I have j, if I put k here, so this is going to become like k, this is going to become like k, this is going to become like k. Wherever I have j, I can replace it k. Okay, so this is going to become like k plus nu, k minus nu, k minus 1 nu, etc. So that's what I got. 2 power 2k, nu plus k minus nu plus k minus 1, etc. Nu plus 2, nu plus 1 is going to be 3. Okay, so same thing. I got written the equation number 4. So 2 power 2k into k factorial into this one. Now we are going to guess this. We are going to get this A0. Okay, we are going to actually any A0 you can do and then you can get it. Okay, so people have used this A0 as some property, and that some particular concept they have used, and then they have simplified this further to get some properties of relations for this Bessel concept. Okay, so some nice properties. But in general, if you take any A0, that is going to occur, because whatever here we assume is A1 not equal to 0 only we assume. You can take any A1 and then you can do that. But in particular case, they have taken A1 is some constant and then they have to. So now nu is any real number. So in particular, suppose if I take nu is equal to some natural number. Okay, nu is equal to here. Suppose nu is some natural number n. Okay, positive real number. So it's a so if nu equal to n, what I can write? So this one I can write it as a to k. A to k is going to become like minus 1 power k into a naught divided by 2 power 2k into k factorial into wherever I have nu, I can replace that with n. So n plus k minus 1, etc. N plus 2 into n plus 2. Okay. So in order to make this nice, what we are going to do is that we are going to make this a naught. Okay. So here already I have one factorial is there, k factorial is there. Okay. Suppose if I put another n factorial here, okay, so that's what they have used. Suppose you put another one n factorial there, then what we are going to get? We are going to get this is going to become like n plus k factorial is going to come. Okay. So again, I am going to use this since there is n plus k factorial. What I am going to do is that I am going to multiply another 2 power n. So therefore this I think 2 power 2n. Therefore this is going to be 2 power 2k plus 1. So that's what they are going to guess it. Okay. So this is going to be your a to k. So one solution you can use this to find. So one solution what you can do is that, so either this case or this case, what you can write is that you can write y1 is equal to y1 of x is going to be summation k equal to 0 to infinity, okay, a to k into x power 2k plus nu, because r is nu, therefore m plus r is going to come. M is here, only 2k term is going to survive, remaining term is going to vanish. Okay, so 2k plus nu is going to come. Okay, this is my y1. So here, if it is nu is something different, then you can use that, or if you choose nu equal to n, then we are going. So now we are going to discuss this case, nu equal to n case, and then this. For that, what is the assumptions we can make? Okay, so for that function, so if I make this nu equal to n, then I'm going to get this y1. So that I'm going to call it as jn. Okay, that is called Bessel function. Bessel functions jn of x. So what is it? What is it going to do? So we are going to do a0. We are going to use a particular solution. So let us choose a particular solution by choosing a0 equal to, as I said, n factorial is there. We can choose. We are multiplying another 2 power n, so that we are going to get some simple form of the equation is going to come. So in that case, what it is going to come? So if I just choose a0 equal to 1 by 2 power n into n factorial, so I will get that. So this is going to become like k factorial is here. So this is going to become like n is going to come. Okay, and here n factorial is going to come. So if I put n factorial there, this is going to become like minus 1 power k divided by 2 power 2k plus n into k factorial into n plus k factorial. Okay. So in that case, if I substitute it over here, okay, so I just erase the rest of the thing. So if I substitute with y1, then I'm going to call that as j1 of x. Okay, y1 of x is going to become like minus summation k equal to 0 to infinity a to k. I'm going to substitute that. So minus 1 power k divided by 2 power 2k plus n into k factorial into n plus k factorial into x power 2k. Nu is already n, so therefore this is going to become like 2k plus 1. So in order to make this as a simple thing, I'm just using that. So therefore this I can write as summation k equal to 0 to infinity minus 1 power k factorial into n plus k factorial x by 2 whole power 2k plus n. Okay, so in order to make that, I'm just using this a0. So this is called this I called as this y1 of x I called as jn of x. Okay, this is called Bessel's functions of the first kind of order n. This is called Bessel's functions of the first kind of order. Okay. So from this one you can find what is j0 of x. Okay, j0 of x is going to become like, so one or two functions you see j0 of x is going to become like, means I got to put wherever n is there, I got to put 0. So this is going to become like summation k equal to 0 to infinity minus 1 power k factorial into k factorial, k factorial into k factorial, x by 2 power 2k is going to. Okay, that is nothing but my j naught of x. Okay, so you can just expand this and then you can get that expression 1 minus x by 2 whole square divided by 1 factorial whole square, etc. Okay. So j1 of x, so if you put j1 of x, then that is going to become like summation k equal to 0 to infinity minus 1 power k factorial into k plus 1 factorial x by 2 whole power 2k plus 1. So that is going to become like j1 of x. So these are all some of the functions usually people will be using it for this electrical engineering and other problems. So this is going to be a series is going to come, and then they will truncate after 7th term or 6th term, and then they will use it for some of the filters. The Bessel filter, if you discuss some of the problems in the electrical engineering problem, they used to do this. Also for the FM analysis, okay, the FM and the FM radios, those days also used. Similarly, this is same thing used for your I don't know, like some of you are geotechnical engineer. So once you are going for this implicit sampling, etc. Okay, where what you will do is that you will just send a signal to the land and then you will get the data out of it. Okay, so in that case also this special function they will use it and then they will get some data and some kind of inverse problems, etc. They will be using it. So there also they used this special function as a tool to solve a particular case. Okay, so there also these special functions are used. Okay, now we'll go for so we deal with the n nu equal to n. Okay, now suppose nu is not equal to n, so nu equal to n means I got chosen a naught is nothing but 2 power n into n factorial I got chosen 1 by 2 power n into n factorial I got chosen. Now if you nu is not equal to n, then also we can deal that case. Okay, for that case what I'm going to do, so see here I have used when nu equal to n case, my a naught I have chosen as 1 by 2 power n into n factorial I have chosen. Okay, so for nu equal to nu not equal to n, okay, nu not equal to n, but it's a positive number. In that case, what I'm going to choose is that I'm going to choose a naught is equal to, so for general nu greater than or equal to 0, I'm going to choose a naught is equal to 1 by 2 power nu, okay, into gamma of nu plus 1. So in that case, you can just check that gamma of n plus 1 is nothing but, okay, gamma of n plus 1 is nothing but n factorial. Okay, this is nothing but n factorial. Therefore, this is going to be satisfied. So if I put gamma equal to n also, that is going to be satisfied. So this is the general a naught I'm going to use, okay, for nu greater than or equal to 0, where gamma is nothing but it's a gamma function. Okay, gamma function which is defined in this way: gamma of x equal to 0 to infinity e power minus t into t power x minus 1 into dx x greater than 0. Okay, so you can put gamma of 0 also going to become a 0 factorial. So gamma of 1 is going to become a 0 factorial, and so nu greater than 0 we are going to deal that. Okay, so in that case you can discuss gamma of 1 factor. So this is nu greater than or equal to 0, nu greater than 0, not nu greater than or equal to 0. So we are going to take that. Okay, j naught of x already we discussed. Okay, j naught of x already we discussed. So nu greater than 0 we are going to take. So then we are going to get this one. Okay, so in this case what we are going to get, so these are the some of the properties of the gamma function you might know. Gamma of 1 plus x equal to x into gamma of x, and gamma of n plus 1 equal to n factorial, and gamma of 1 by 2 equal to square root of pi. Okay, and gamma of n plus 1 by 2 is going to be this term n 2n minus 1 factorial by 2 power 2n minus 1 into n minus 1 factorial square root of pi. So these are also you might see these properties of the gamma functions. Okay. So we are going to apply the similar kind of thing over here. So in this case, what you can expect is that so a2k is the same thing. Whatever I talk here, okay, this one is going to become like, I'm going to rewrite this one as. So this one is going to become like, I have a naught is 2 power nu into gamma of n plus nu plus 1 is going to come. So this is going to become like, I'm going to write this as k factorial is already there. K factorial is there already, and I have 2k plus nu is going to come. So I'm going to put the nu here, okay, and then I'm going to put a gamma of nu plus 1 here. Okay, So I can just push that. Okay, so this is everything wherever I have n, that is going to become n. So this is going to be u case. Okay, it's not u equal to n case. So this is going to be new case. So wherever I have n, that also I have to replace with new. Okay, I replace that as new. So we have this property. Okay, the gamma function property. So take the first property, x into gamma x is going to be 1 plus x. Therefore, this is going to become like nu plus 1 into gamma of nu plus 1. So this is going to become like nu plus 2 gamma of nu plus 2. Okay, so this is going to become like nu gamma of nu plus 2. Now if I choose these two terms, this is going to become like gamma of nu plus 3. So like this, you can keep on decreasing. Okay, you can keep on reducing one of the term, one by one term. So at the end, what you are going to get, at the end you are going to get something like nu plus k into gamma of nu plus k is going to be. Okay, but what is that nu plus k into gamma of nu plus k? That is going to become like nu of gamma plus gamma of nu plus k plus 1. Okay, so therefore a to k I can write as, okay, a to k I write it. A to k is going to become like minus 1 power k divided by 2 power 2k plus nu k factorial into gamma of nu plus k plus 1. Okay, so once again I can substitute this equation. Okay, wherever I have that, so that is going to become like y1 of x. So this erase first. So this is going to become like summation k equal to 0 to infinity minus 1 power k factorial gamma of nu plus k plus 1 into x by 2 whole power 2k plus 1. So this is going to be my j. This I call it as, okay, this one I call it as, this is called as j nu of x. Okay. So we have j n of x and this is called j nu of x. So j n of x is going to become a particular case of this one. Okay, that's what this is called. Bessel functions of the first kind of order. So gamma equal to nu, sorry, nu equal to n. If I put nu equal to n, that is going to be j n of x. Okay, that's a particular case of this one. Also, people used to write this as this way because this nu is independent of that. So I just write this as x by 2 power nu. Okay, they take only this term out, and then the remaining thing they just whatever k terms that they use. So minus 1 power k factorial into gamma of nu plus k plus 1 into x by 2 power 2. Okay, so that is also okay. So these are some of the properties of the Bessel's function, which I leave it as an exercise. Okay, some problems may be in assignment, some problems may be in the tutorial problems. So these are some of the properties of the Bessel's function, like j0 dash of x is going to be j1 of x, and these properties are going to be useful for deriving our second Bessel functions of second kind also, which we call as y nu of x. That also we are going to deal with. So in that case, one of these properties will be useful. We are going to use that. Apart from that, there are some other properties, like if you take x nu into j nu of x whole dash, that is going to become like x power nu into j nu minus 1 of x. There is a relation between j nu and j nu minus 1. Similarly, there is a relation between j nu and j nu plus 1. Okay, the derivative of, if you take the j nu derivative with some adjustment, you are going to get j nu plus 1. Similarly, there is a relation between j nu minus 1 and j nu plus 1, and that is another property. Okay, there are two properties there. One is with respect to j nu, another is with respect to j nu dash 4 and 5. Similarly, j nu dash and j nu, if you submit 4 and 5, from 4 and 5 you can derive that. If you just subtract one of them, then you can get that. If you multiply and subtract, you will get the sixth one, which is easy one. From 6 to 1, 6 to 1 is very easy. From 4 and 5, if you prove 4 and 5, then you can get that. 7th one is also you can prove that. So j half of x. So wherever I have nu, you put it half over here, and then find the answers for that. That is going to give you the sin x series. If you take some square root of 2 pi by x, because once you expand here, you are going to get 1 by 2 half plus k plus 1 is going to come. So you expand it here, then you are going to get you are going to use this relation, whatever you have here. this property n plus 1 by 2. So if you use that over here, okay, instead of n plus 1 by 2, you are having r. So if you use it over here, then you are going to get that is going to become like sine 2 pi x term is going to be. Okay, so remain you take root pi and 2 pi x outside, and you are going to get because x power 1 by 2. So mu is 1 by 2. So this is going to become like 2. So if I put 1 by 2, this is going to become like x by 2 whole power 1 by 2 is going to come. So here also you can take some of the terms out. So that is going to become like, if you take x, I think it will become like x power minus 1 by 2. So that is going to become like 2 by x. So you will get the answer as sin x. So this is also simple one. So you can straight away use this one other way. So one of these problems will be asked in the Saturday exam. And j minus half of x, similar kind of things, you can prove that this is going to be like 2 square root of 2 pi by x cos x. Okay. Now let's go for the Bessel functions of second kind. Okay. So for second kind, what we have, so far we discussed r equal to mu case only. So far we have discussed. Okay. So r equal to minus mu case. So far we haven't discussed. So those cases we are going to discuss now. Okay. So for r equal to minus mu, and this mu does not belong to z plus. That is another thing you have to do. Okay. Because 2 mu does not belong to z, so therefore we can just find a second linearly independent solutions we are going to get. Okay, so how we are going to find that? So for that, if it is r is minus mu, we are going to extend it from here. Okay, so if we can extend it from here, what we are going to do when r equal to minus mu, okay, when r equal to minus mu and 2 mu does not belong to z plus. Okay. That case, 2 mu does not belong to z plus. In that case, I can deal this case. Okay, so in this case, I am going to write the same set of 1. Wherever I have mu, that I can write as minus 2. Wherever I have mu, that I can write as minus 2. So that is why it becomes j minus mu of x is going to become like x by 2 power minus mu. Okay, and summation k equal to 0 to infinity minus 1 power k divided by k factorial into gamma of minus mu. So I'll put minus mu plus k plus 1 into x power 2, x by 2 power. Okay, so this is called this is the second solution. Okay, we are going to see that about y mu of x, etc. So we are going to do that. So this is called j minus mu of x. Okay, so here you can see that these two are independent solutions because here I have nu, here I have minus nu. Okay, here I have nu, this is going to be minus nu. Therefore, this cannot be generated by this one, or this cannot be generated by this one. Therefore, these two are completely independent. Okay, completely independent means they are not, one cannot be generated by another. Therefore, these two are going to be linearly independent solution. So, in that case, my general y of x, in this case, my general y of x provided 2 nu does not belong to z plus y, that is the case. We'll see that in the next one. So, in this case, I can write y of x is going to be some c1 into j nu of x plus c2 into j minus nu of x. That is going to be my y of x. Okay. So this is going to be my general solution for the Bessel equation for all x not equal to 0 and 2 nu belongs to z. Okay. This is one property which I want to specify because probably this is used in the next one. So Bessel's functions jn of x. Okay. So we'll do that because I need to say what is minus n, then only I can define that. Therefore, I'm going to see that. So we know that gamma of n tends to infinity of n belongs to z minus. Okay, that we know that. So now what we are going to do, we are going to see the first n coefficient approaches 0. So therefore, what is going to come? Gamma of n minus k plus 1. Okay, that is going to be 0 for all k less than 1. So what we are going to do, so in that case for this one, okay, so if I put gamma of n minus k plus 1 or minus n plus k plus 1, so in that case what is going to come, or even take the this one, so what is going to come, this is going to tell you first n terms are going to become 0. Okay, when n k is less than 1, the first term, because gamma n tends to infinity, the first n terms is going to become 0 because you are having gamma n tends to infinity. This is in the denominator. So first two n terms are not going to exist. That is become 0. Okay. So therefore, what you are going to get? You are going to get is first. This is one simple problem which we solve. Okay. So let us give this j minus n of x. So j minus n of x, as per the definition, what I have is that I have x by 2 power minus n summation k equal to 0 to infinity minus 1 power k x power x by 2 power 2k divided by k factorial into gamma of minus n plus k plus 1. Okay. So now, if you see here, okay, so this I can write as minus n plus k plus 1. So if you see here, okay, so in this one, first n terms, okay, first k terms, it is going to become 0 because it is not going to survive over there. It is not going to survive because of when k, then gamma n tends to infinity, because this is going to dominate that. If k is less than n, okay, if k is less than n, then what I am going to get? Minus n plus k is less than 0. Okay, n plus even k plus 1 also I can just say, okay, this is going to be there. So this is going to be less than 0, or even take k plus 1 also, that is also going to become like less than 1. So in that case, this is going to become like, it's not going to survive up to that time. Okay, only when n equal to k, it is going to survive, otherwise it is not going to survive. Till less than n, it is not going to survive. Okay, so because you are going to get when k equal to n, when k equal to n, you are going to get gamma of 1. When k is not equal to k is less than n, you are going to get less than gamma of 0, I don't know, gamma of minus 1, gamma of minus 2, etc. is going to come. So in that case, I don't know what is the. So in that case, we have already assumed that gamma n tends to infinity if minus means negative part. Okay. So therefore, what we are going to get, when k equal to n, it is going to survive. Remaining term, it is going to be infinity. So this is going to 0. Okay, since it is in the denominator, this is going to 0. So therefore, I can write this as x by 2 power minus n, k equal to n only, it is going to start. It is not going to survive for k less than n, it is going to start from k equal to 1, n only. Minus 1 power k, k factorial into gamma of minus n plus k plus 1 into x by 2 power. Okay, so in that case, I can just I'm just going to multiply. What I'm going to do is I'm going to multiply some 2 power n on both sides. Okay, x by 2 power n I'm going to multiply. So this I'm just doing some simple manipulation. So x by 2 power n I'm going to multiply summation k equal to n to infinity. So I'm going to multiply minus 1 power k k factorial gamma of minus n plus k plus 1 let it be. I'm going to do here x by 2 power 2k minus n, x by 2 power n I'm going to do. So I'm just multiplying, sorry, 2n, I think. Yeah, 2n. Okay. So I'm just multiplying and dividing by x by 2 power 2n. So this is going to be x by 2 power 2n. So I can take x by 2 power 2n outside. So this is going to become like x by 2 power n. Why I am multiplying? Because if you remember the j nu of x, j n of x, in that case you know that you are going to x by 2 power nu is going to come. Means I got to get x by 2 power n. Therefore, if I multiply by x by 2 power n, therefore minus n and plus that is going to become like x by 2 and this is going to become like summation k equal to n to infinity minus 1 power k factorial into gamma of minus n plus k plus 1 into x by 2 power 2 into k minus 1 n. Okay. So now I can just since k is starting from m, k equal to m, I can just put this as again k minus n equal to 0. I can start. Okay, k minus n I can start. So in that case, once again I can do the simplification of all these things. Okay, so then I'm going to do x by 2 power n summation. This k equal to n to infinity same as k minus n equal to 0 to infinity because both are same. K minus 1 power k by k factorial into gamma of okay, so x by 2 power k minus 1. Okay, that's fine. So now I am going to do some more manipulation. Okay, so this k factorial I can write as k minus n plus n factorial I can write it. Okay, k minus n plus n factorial, that is same as k factorial into gamma of this. Also I am going to do some k minus n plus k is I am going to subtract r and subtract. Okay, minus n plus k is there. So I am going to do minus n plus addition minus n plus k minus n plus n plus 1. Okay. So I'm going to simplify this further. So this I can write it as x by 2 power n summation k minus n equal to 0 to infinity minus 1 power k. Okay, minus 1 power k. One more time I go to r and subtract. Let me see what I got to do. Okay, so similarly I can just add here. Okay, minus 1 power n minus 1 power minus n I can put. Okay, so in that case this is going to become like minus 1 power k minus n. I'm going to take this minus 1 power n out. Okay, minus 1 power n out into, so remaining thing I'm going to write. So this is going to become like minus 1 power k minus n. Okay, this is going to become like minus 1 power k minus n divided by, so this I can write as k minus n plus n factorial. This I can write as minus n plus 1. You see, k minus n factorial, k minus n. Okay, n get cancelled. Okay, this n get cancelled. So just same as this one. You don't need to multiply here. Okay, you don't need to subtract r and subtract here. That's same thing. K minus n plus n factorial is that. Okay, so this I am going to simplify further. So I am going to replace. Okay, this I am going to replace it as wherever I have k minus n, I am going to replace that as minus 1 power n x by 2 power n. I am going to put as, because these are dummy notation, I can just put s equal to 0 to infinity. Wherever I have k minus 1, I am going to put s equal to 0 to infinity. Therefore, this is going to become like minus 1 power s divided by s plus n factorial into gamma of s plus 1. Okay. Okay. So gamma of s plus 1, because I am taking n, s is also here. So this is going to become like this gamma of s plus 1, I can put it as s factorial. Okay, I'll write here. So this is going to become like minus 1 power n x by 2 power n summation s equal to 0 to infinity minus 1 power s divided by s plus n factorial. Okay, into s factorial, because gamma of s plus 1 is s factorial, so that I am going to write as s factorial. And this is again I can take it as a, I can just rewrite this as gamma of s plus n factorial, that I can write as, it's going to become like summation s equal to 0 to infinity. Okay, same thing here, minus 1 power n x by 2 power n minus 1 power s divided by s factorial into gamma of s plus n plus 1. Okay, because s plus n factorial is nothing but gamma of s plus 1. So this s is again a dummy index, so I can replace this as k. Okay, this is going to be k, this is going to be k, this is going to be k. So this, if you just concentrate this one, this is same as this one. Okay, so here I missed this x by 2 power n is, this is going to be there. Okay, x by 2 power 2k minus 1 is going to be there. Missed that, so you can just write that. Okay, x by 2 power 2k minus n. This is going to be x by 2 power 2s. Okay, here also x by 2 power 2s is there, and here this will become x by 2 power 2k. So same thing as this one. Therefore, this is going to be minus 1 power n into j n of x. So j minus n of x is same as minus 1 power n of x. Okay. This I will stop. Some more second kind we have to deal that. So this I will deal it in the next class, and then we will solve some of the tutorial problems also on Friday, and because that will be helpful for your end semester, sorry, the Saturday's exam. So I'm going to discuss some of the tutorial problems which is in the next tutorial. Okay, so that also will discuss in the next class.